Thank you very much for inviting me to give a presentation here today. I'm going to talk about results from a study looking at transport of ammonia through a topographic gap between the Utah and Salt Lake basins. And I want to acknowledge my co-authors, Eric Crossman and Randy Martin, and the funding from Department of Environmental Quality here in Salt Lake in Utah. So introduction, motivation. This is, we've heard about this, of course, before in this lecture series. We all know that the Salt Lake Valley and other basins here in Utah are struggling with non-attainment for PM 2.5. We learned a lot, again, yesterday about the adverse health effects for both short and long-term exposure. We know much about the chemical composition, that ammonium nitrate, the secondary pollutant, dominates during the strong pollution episodes. And we also learned just now again from Gannett that there's still work to do regarding the reactive pathways for ammonium nitrate formation. And also their dependence on meteorological processes, the role of different oxidation processes and so on, of the NOx to nitric acid and so on. And we also learned today about potential role and sources of ammonia. So this morning there were some interesting talks. On the meteorological side, we know that wintertime pollution episodes are closely linked to persistent cold air pools. And in previous purely meteorological studies, from those we know about the life cycle of these persistent cold air pools, and that there's different versions with clouds and clear ones, and that affects the temperature profile and so on. And that we know that might have an effect on the chemistry as well. The valley heat deficit is a concept that's very helpful to quantify the strength of these persistent cold air pools, and that has been related to PM 2.5 concentrations. Now, however, there's still little known about spatial and temporal variations on smaller timescales than 24 hours, or on timescales of the life cycle of persistent cold air pools that need attention. And also, we need to know more about the driving, transport, and mixing processes that might distribute pollution and precursor gases. So persistent cold air pools are typically characterized by limited mixing. However, in previous experiments, we have identified, and it has been identified, that some mixing and transport processes can occur. And here I made a slide for nighttime conditions and of daytime conditions of these persistent cold air pools. And I'm moving this back and forth a little bit to highlight these processes that are known. And for instance, the thermally driven slope and valley circulations through the tributary canyons have been qualitatively shown to play an important role. So typically we see injections of low PM, but also high ozone air at the mouths of these tributary canyons. We know that thermally driven and synoptically forced air mass exchanges with the Great Salt Lake play a role in modulating air quality in the Salt Lake Basin. We know that daytime vertical mixing, buildup of development of a convective boundary layer near the surface at the bottom of the cold air pool can lead to vertical mixing. And then we know that this often decouples at night, and we have a decoupled surface layer at night. For all of these processes, we have good qualitative observations. However, what we really need to think about is if we want to understand more about the budgets of pollutions and pollutants and precursors, we need to start quantifying their relative impact to evaluate their importance. So I had the opportunity, thanks to funding from DEQ, to have a look at one other transport or exchange mechanism. That is this interbasin exchange here, and at the interface between the Salt Lake and Utah basins. And this time I tried to not just do some qualitative observations, but actually try to quantify the effect. So the Jordan Narrows Gap Ammonia Transport Study was a piggyback study on the Wasatch Front Ammonia and Chloride Observation Study, WAFACO. And basically we added some meteorological observations to the Jordan Narrows. The Jordan Narrows is the basically the topographic gap in the transverse mountain ranges between the Salt Lake and Utah Valley. We analyzed existing and study-specific meteorological data sets, and we also provided forecast support for the WAFACO science team. And the ultimate goal was to develop or try to develop a methodology to investigate this air mass exchange. And then by adding information of surface concentrations to try to see whether we can develop a methodology to investigate ammonia transport or between the Salt Lake and Utah valleys. The main observations were a Doppler Wind LiDAR, the University of Utah Doppler Wind LiDAR that we deployed at Camp Williams in the Jordan Narrows, and we added some automatic weather stations right there in the Jordan Narrows on the shore of the Jordan River. And we had a ceilometer network, which I'm not going into detail today. And then we added an automatic weather station to the north of the gap, and we could also rely on other Mesowest weather stations. For example, this weather station Flight Park South, which is marked here, which is on a bit elevated within the Jordan Narrows here on the Traverse Mountains. So a very simple methodology was developed. All of you could have come up with this. Basically, what we have is a topographic data set, a digital elevation model. Then we have a wind profile that we are calculating retrieval from the wind LiDAR. We have some concentration measurements, in this case of ammonia from WAFACO. And then we use, like we typically do in science, a lot of assumptions. So here's a example, a cross-section that can be calculated to a gap. And we have the wind field, the wind profile within a flow layer. And then we use concentrations within this flow layer. And we have to project, of course, these concentrations within to this flow layer. So for the topography, what we did to come up with defining the topographic gap, we basically used the mean wind direction. And I basically put perpendicular cross sections through the topography and end up defining here this a cross section of the interface between the Salt Lake and Utah valleys, the Jordan Narrows. And these are all these different cross sections, basically that maximum elevation here defines the Jordan Narrows. And by doing these calculations, I can define a gap width as a function of height, a gap area as a function of height, and I also could calculate the Salt Lake Valley basin volume. And what I want to highlight here are two different elevations. So that is 1,800 meters above sea level and 2,200 meters above sea levels. And those are elevations, the 1,800 meters, basically the level where the Jordan Narrows are really defined just within the river basin of the Jordan River. As soon as we go above this elevation, actually, there's also air mass exchange through low gaps within the Traverse Mountains. 2,200 meters is typically considered as the average ridge height around the Salt Lake Basin, and also that's the height the heat deficit is typically calculated for. So here's some results now from the wind retrieval, and what I'm showing here is a time height cross section of the flow field at the Jordan Narrows for an 8-hour period, and I selected that period not randomly, because it's actually quite interesting wind field here. So that was on the 24th of January 2019. And what you see here is actually that there's flow field in both directions through the Jordan Narrows. And again, here I'm highlighting the 1800 meters and the 2200 meter heights. And you see that near the surface, the near surface flow is actually southerly in this case. So we have flow from south to north, from the Utah to Salt Lake County. While above the Traverse Mountains, we're actually seeing a northerly flow. So flow from north to south, from Salt Lake to Utah County. So it's actually a very interesting conditions here in this case. And we have this reversal of the flow. So once we have the wind profile, we can calculate the gap normal flow component and use the gap width to calculate the volume flux through the gap as a function of height. And here you see a contour plot of this volume flux. So again, a time height cross section. And you can see that near the surface, we're having a southerly flow, and on the top we have a northerly flow. You see these values are higher here above. First of all, we have higher wind speeds, but also our gap width is wider. So that is the reason for this. So once we have the volume flux as the function of height, we can now integrate that to different elevations. And here in this case, I'm showing time series of the integrated volume flux, both integrated to the 2200 meter level and the 1800 meter level here in this case. And you can see that if we only look at the surface-based flow layer, we see that in this case a southerly flow dominates, and we can basically get here volume flux in cubic meters per second. If we are integrating to 2200 meters, we're again seeing that the northerly flow in this case dominates because of the gap width and the higher wind speeds. So now that we have a method to determine the volume flux, we need the last ingredient, and those are concentrations. And this is a brief introduction to the observations that Randy Martin did and provided here. Those are ammonia concentrations taken at Camp Williams at the same site where the LiDAR was positioned. And you can see that there are times with elevated ammonia, which is here highlighted in gray. And they are not extremely high, but they are definitely elevated. The second time series here, you're seeing a time series of temperatures at Camp Williams, Flightbuck, South, and Bluffdale. And in black, what I'm showing here is basically a potential temperature gradient, which is a measure for the atmospheric stability during these times. And in the bottom, I'm showing wind speed observations. And what I want to highlight here is, as we expect, during periods of elevated atmospheric stability, we are expecting buildup of surface emissions, such as from ammonia. And typically, after then the wind speeds increase, we're seeing the spikes in the ammonia concentrations, or the elevated ammonia concentrations. So to get to the final calculations here, now we can use the volume flux of through the surface-based flow layer. We can multiply it by the surface concentrations and actually calculate a mass transport here, in this case of ammonia. And what I'm showing here is a time series for these 2 weeks during which ammonia observations were made in the Jordan Narrows Gap. And I'm basically showing here the transport below the 1800 meters, so really confined in the Jordan Narrows proper. And I'm plotting here now the ammonia flux in gram per second, or in metric tons per day. And what you see here is that during that 14-day period, typically we saw southerly transport. So the southerly transport dominated. So we had transport from the Utah Basin to the Salt Lake Basin. But there were times too when the the transport was dominated from the Salt Lake Basin to the Utah Basin. Now, what is actually interesting, and was a bit surprising to me, is actually when we compare these values with average wintertime daily emissions from Utah County and Salt Lake County is that we can see that daily averages here indicated with these horizontal bars for these days. It really looks like this interbasin exchange is actually quite significant and might play an important role in the budgets. So interbasin transport is something that probably needs to be taken into account in future investigations of the precursor budgets. So with this, I want to, as a summary and conclude, we use a combination of Doppler Wind LiDAR, wind retrievals, topographic calculations, and surface-based measurements of ammonia to estimate transport of ammonia through the Jordan Narrows, and basically the exchange of ammonia between the Salt Lake Valley and Utah Valley basins. During this limited 14-day period, we saw that southerly flow dominated. Our estimates show that the ammonia transport is significant when compared to average daytime wintertime emissions from both Utah and Salt Lake County. And so to quantify that, like on average on those 14 days, Utah County exported about 20% of its daily ammonia emission through the Jordan Narrows into the Salt Lake Basin. And in turn, Salt Lake County imported an additional 45% of its own emission by means of this interbasin exchange. I want to highlight that there were a lot of assumptions used in this methodology, and the representativeness of the surface concentrations when estimating the concentrations in the flow layer could be refined, maybe by future evaluations. I also want to quickly mention that as ongoing research, I recently got funding to use a similar methodology in the Red Butte Canyon drainage to investigate the transport of particulate matter and ozone through these tributary, as an example of a tributary canyon. And I want to highlight that more quantitative estimates of pollution and precursor transport are needed to understand their budgets on a basin scale. And as Gannett mentioned, the upcoming planned Aquarius project might be ideally suited to evaluate the relative importance of these identified transport and mixing processes. And with that, I want to acknowledge the funding again, and I'm happy to take questions.
Terrific, thank you.